I would love to just kind of talk a little bit about the philosophies that we have at Beta, share with you some of the work we've been doing, and then just have an open discussion about how we're approaching the Agility Prime mission needs and the aircraft development. So I'll be short on the front end and talk a little bit more on the back end. So I'm just going to attempt to share my screen again here, and if somebody can just give me one thumbs up so I know that you can see it, that would be awesome. Thumbs up. Can you? Oh, we've got one thumbs up. Thanks, Greg. Good stuff. So let's go here, and just to extend on some of the stuff that I was talking about in the Firestarter, which, by the way, I think is a very inappropriate name for aircraft. The first principles engineering approach that we're taking to aircraft development really centers around the respect of the challenges associated with electric propulsion. And as many of the people on this call I know, we are really penalized in energy density. Although it is growing, we're still going to be struggling with getting to the energy density of liquid fuels. And I think it's important for us to recognize that electric aircraft does not just mean that we're storing it in batteries or converting, or doing some type of battery-based system. It could mean hydrogen fuel cells, it could be other types of batteries, and of course it could be overall hybrid systems. But either way, we need to carry a lot of energy and convert it efficiently. But as I mentioned before, and this is where we'll kind of jump into some of the stuff we've developed, this is a relatively low quality, now that I see it up close, the picture of a recharging pad. And I want to answer a couple questions that people commonly ask about why a recharging pad. And this stems from the recognition that storing 300 to 400 kilowatt hours of battery on an aircraft, and in this particular case, our aircraft is designed for a relatively long mission of 200 plus nautical miles. To make that system commercially viable, it needs to recharge very quickly. And over on the right side of this recharging pad is all of the flight test batteries from our first several campaigns acting as arbitrage or big buffers to the electric grid, such that when the aircraft lands to charge, the energy is actually sloshed from the stationary storage batteries over to the batteries on the aircraft. And the utility grid, most of which are fairly constrained because historically airports are not big consumers of power, sees a very, very small perturbation in its load, from a trickle charge to a trickle charge of the arbitrage batteries to a trickle charge of the aircraft batteries, with the majority of the energy being produced for the aircraft from the storage batteries. And what's really interesting about this is that once the aircraft leaves, because there's an active front end, i.e. a 4-quadrant inverter tied to the electric grid, providing 3-phase real and reactive power, we can then provide support services of the grid. And the dirty little secret of providing support services are that if you want to put a diesel generator on the grid to support things like electric car recharging or airplane recharging, and you want to swing up and down by a megawatt, you have to put a full 2 megawatts in, and you operate nominally at a megawatt, and you absorb some. You can't absorb any energy, so you just lower the production, or you increase your production. With batteries, because they're bidirectional, you can both absorb and supply. So per nameplate, per megawatt we install, we can provide twice as much services, which means twice as much revenue for the recharging pad when it's on the grid. The other question I get is, why does it have an elevated deck? And in this particular case, this example is actually inside the side of fence of the Burlington Airport, not necessary to have an elevated deck, but in many, many cases at hospitals and parking lots and urban environments and industrial parks, the security of the landing zone, especially as we transition to unmanned flight, is very, very important. So the elevated deck provides that first and foremost, but the second effect is, in this case, for example, it provided our compliance with the FAA advisory circular on the approach and departure angles and clearance zones. So we don't have to go chopping down fences and trees and organizing 300 foot of clear area before you get to the pad. And that's a really big deal, obviously. The entire system. Yep.
Sorry to interrupt. We're at the 5-minute mark.
Oh, okay. Well, I'll do another 30 seconds. talk about avionics, and I think this is, I brought this up only to point out the fact that systems management in electric aircraft is significantly different than systems management in a turbine or a gas-powered aircraft. And so a huge amount of effort has gone into developing with the FAA's cockpit integration team, crew loading systems and other propulsion management systems. And I'll stop there. I think that a lot of this stuff is old information. This was our test mule of power electronics, batteries, motors, inverters, a couple hundred test flights on it. And this was our test mule that we used for developing ground power, recharging, and controls. So I'll stop there, and we can jump into some questions.
Thank you, Kyle. We've got a couple of questions, actually more than a couple of questions. You've got a lot of questions. First from Jeff, how are you addressing see/sense and avoid in cruise and in urban?
Yeah, so we have a philosophy that as pragmatists and pilots, that we're first going to cross the threshold of deploying an electric aircraft and then worry about those other things like sense and avoid. Fundamentally, we're tracking those technologies, the LiDAR systems, the optical systems, even ground-based cooperative systems, so that we can collect data from other sensory suites. But frankly, the primary development we're on is to fly a 6,300-pound aircraft with significant cargo on it, and not worry about sense and avoid yet, because it's going to be a piloted aircraft to start with. And in 2025, after we have this thing certified and rolled out, we will be adding those features. So we're providing the provisions right now, but not exposing those or exploiting them.
Great, thank you. Next question from Rachel. Hi, Kyle. I'm curious about Beta's involvement in hydrogen tech. Also wondering if you can further explain your trickle charging arbitrage and how it relieves the constraint of grid draw.
Yeah, so we are tracking fuel cell technologies and other hydrogen power systems, but our focal point, just to get this thing in the air, is around batteries. So we've met with several companies, looked at the specifications, and mostly shied away from it because of the reliability and complexity of those types of energy storage systems. With respect to the grid draw, every grid has a base load and a supplemental load that is usually consumed by very, very fast changing things like cycling pumps and compressors and presses. And that cyclical load at the top of the grid is usually serviced with peaker plants that are super inefficient, very expensive for the utility. So with the arbitrage batteries in the grid and the 4-quadrant inverters, which means that it can push and pull at any phase shift, real and reactive power, it can then be dispatched by the utility, and providers absorb that power to keep the grid frequency and voltage stable without having diesel generators polluting.
Okay, thank you. Probably one last question. If we've got more time, we'll do another one. But the next question is from Arush. Can you elaborate on what you said in the keynote about so many components not belonging on the aircraft?
Yeah, sure. It's my favorite question, actually. The unique airspeed and operational corridor of a vertical takeoff and landing aircraft tells us that we don't need certain things: flaps, slats, speed brakes, retractable gear, and that other things can be solved more elegantly, like gearboxes, liquid cooling, tilting wings, variable pitch props. And I'll just use that one last example of variable pitch props or articulating rotor heads. We found through extensive design studies that we made a big mistake on our first vehicle. We assumed that a tilting rotor, a thrust vectoring system, would be inherently more efficient because it was less weight, less components, and we could reuse for both cruise and hover. And our latter vehicle is a lift plus cruise, and the studies show very clearly that optimizing a rotor for lift and a different rotor for pushing allows you to have an overall net benefit in the efficiency of the vehicle, because the twist and the pitch, two very important and different things, can be point designed for lifting or pushing. And that allows us to say, you know what, we don't need that stuff. And we leave flaps, variable pitch props, thrust vectoring, anything that moves off the aircraft. And as I mentioned in the keynote, that makes for the lightest components because they don't exist, and the most reliable because they can't break. So our vehicle, it'll pick itself up with only 4 moving parts, and it'll fly forward with just traditional flight surfaces and 1 pusher.
All right, Kyle, one last fun question from Mark. It's rumored that you were once a professional hockey player. Is this true? And if so, how does this connect with the creation of Beta?
That's funny. I played on the U.S. junior team, and then went to college and played there, and then was drafted by the Capitals and had a very, very short professional hockey career. But I think the interesting part of that, I guess, I could dig out 10 of them, was that when I had always dreamed of flying. I had built a ultralight in high school, and my mother burned it, so I didn't kill myself in it. Tried to go flying every chance I got at the local airport by helping the mechanics. But the day I got my signing bonus, I went straight to the airport and paid for my entire pilot's license in one shot, because it was a dream that I had always not been able to afford. So hockey kind of enabled my passion to materialize in flying.
Great.
Very awesome.